Welcome. So in this video we are going to use L'Hopital's rule to solve limits where there's an indeterminate power. So if I have the limit of f of x to the power g of x, so f of x to the g of x, we say that it's an indeterminate power if that limit is of the form 0 to the infinity, infinity to the 0, 0 to the 0, or 1 to the infinity. The idea is that we cannot evaluate this limit directly by looking at its form, but we will rewrite it so that we obtain something that's easier to work with. The key point is to use the identity u equals e to the ln of u. Now the exponential function and the logarithm function are inverse functions of each other, so when I compose them together, I get back the identity function. I get back the function that's just u all the time. Replacing u by f of x to the g of x, we get that f of x to the g of x is the same thing as e to the ln of f of x to the g of x. And the other thing we'll do is send the power here in front of the logarithm. That's something that we can do due to a property of logarithms. And the key point is by doing that, the exponent will now be g of x times ln of f of x, and it will typically be an indeterminate product once we've rewritten our initial expression. And we know that we can solve indeterminate product by using L'Hopital's rule. As an example, look at the following limit. It's the limit as x goes to infinity of 1 plus 1 over x to the ax, where a is a positive number. It's a limit of the form 1 to the infinity, because the base, 1 plus 1 over x, goes towards 0, and ax goes towards infinity. We use our identity to rewrite the expression as e to the ln of 1 plus 1 over x to the ax. And we send ax in front of the logarithm, getting e to the ax times ln of 1 plus 1 over x. It is now the form e to the infinity times 0. So the exponent is an indeterminate product. That's because ax goes to infinity. And because 1 plus 1 over x is approaching 1, ln of the entire thing is approaching 0 due to the fact that ln of 1 is equal to 0. So we should try to evaluate the limit of the exponent by sending either ax or the logarithm in the denominator. In a previous video, we had an example where we had a polynomial times a logarithm function, and what worked for us was sending x in the denominator. We should try to use that same strategy. It might not work, but because it has worked in the past, that's my first pick. So if I send x in the denominator, it becomes x to the minus 1. X to the minus 1 goes to 0 as x goes to infinity. The numerator is going towards 0. So we have a limit of the form e to the 0 over 0. And the idea is that because the exponent is of the form 0 over 0, we can use L'Hopital's rule. If we differentiate the numerator, think of that as ln of u. Its derivative is 1 over u times u prime. U prime being the derivative of 1 plus 1 over x. The derivative of 1 is 0. The derivative of 1 over x is the same as the derivative of x to the minus 1, and that's minus 1 x to the minus 2. And we get that also in the denominator because we're differentiating x to the minus 1 as well. So these two factors cancel out. We can simplify our expression. It becomes this. As x goes to infinity, 1 over x goes to 0, and the entire expression goes towards e to the a times 1 over 1 plus 0. That's simply e to the a. So for instance, if I replace a by 3 and compute e to the 3 with my calculator, I get 20.086. And what this limit says is that if I replace x by my favorite large number, I've chosen 10,000 to see what I was going to obtain, I get that the expression is 20.083. So you can see that when x is 10,000, this is pretty close to the actual value of the limit, which is e to the 3. Thanks for watching.